stop here because at least it was vinegar. And I took a swallow of vinegar, well, I spit out most of it, but I had a little bit of vinegar. Well, vinegar is not gonna kill me, one. And two, I get calories from vinegar, and so I got some calories. If it stopped here at acetaldehyde, I would have been in trouble because acetaldehyde is gonna cause you headaches and hangovers and just acetaldehyde is also toxic, I mean, it's a toxic chemical, like formaldehyde.
So do you not eat vinegar? Do you not like vinegar?
I like vinegar. I eat lots of vinegar. There's no problem. Vinegar I like. I just don't want to drink it.
Oh.
That's all. So there are people who drink it, and they get calories from it, right? They drink it for energy. But the thing is how do I stop here? How can I stop here? How can I stop here? How can I stop there? Right? How do I stop? Well, that depends on the conditions. So I asked you this question before. I want to burn my methane and I want to just convert it into soot. I want lots of soot. How can I do that? You know, can you tell me where I'm going to get 100% soot? Or rather than that, you know what? I want carbon monoxide and I want only carbon monoxide. Can you tell me how I'm going to get carbon monoxide? No. Typically what we do is when we burn it, we just try to burn it all the way to CO2, carbon dioxide. Because otherwise we have to play around with the conditions. Because I told you this before, and it depends on the conditions. So if you're taking organic chemistry or if you're taking biochemistry, you have a whole slew of oxidizers, from mild oxidizers to strong oxidizers at low concentration to strong oxidizers at high concentration. And in organic chemistry, you know, they played around with it enough to know under these conditions, you'll only oxidize it part way. And we want to stop it here. We don't want complete reaction. We want partial reaction, right? But those conditions are mostly generated from theory or mostly generated from trial and error and experiment. Most of those conditions are generated from experiment, you know, just trying it and seeing what happens. That's it, try it, see what happens, you know. And so you could do the same thing here. You screw the barrel in and you see what happens. But, you know, since those depend on prediction, based on trial and error, then what we have here is this situation. This is partial metathesis. This isn't complete. And so, you know, if we want complete, you know, what happened here was, you know, it's going to form calcium, sulfate, and phosphoric acid. But, you know, we just stopped one hydrogen shy of phosphoric acid. Do you see only 2 hydrogens made it? We needed the 3rd hydrogen. And so this is incomplete reaction. So you go, wait, this was incomplete reaction. You shouldn't have stopped here. You shouldn't have stopped here. But why did they stop here? They stopped here because this is what they wanted. They wanted calcium, what do you call this stuff? They wanted calcium dihydrogen phosphate. They wanted calcium dihydrogen phosphate because, you know, phosphoric acid?
Bad.
Well, phosphoric acid is not too bad, except it's a liquid. And it's a liquid that loves picking up water from air. And so phosphoric acid is very difficult to handle. In other words, it's a huge pain. Whereas if you have a salt like this, it's a lot easier to handle. This salt should probably be soluble. You want the phosphate to go on the ground. So this one is called superphosphate fertilizer. And so they intentionally stopped here. So they must have done some trial and error to predict, you know, how they can get the maximum yield of superphosphate. However, we wouldn't have done that. You know, we would have done this equation like this. And so I want to make mention of this because if you know, when you look at these things, you want to, you know, like, who was that guy who said chance favors the prepared mind? You know, the guy who discovered penicillin.
Oh, Fleming? Well, no, is that Alexander Fleming?
Fleming?
I believe so.
Okay. Well, you know, this is it. Chance favors the prepared mind. So a lot of people will see this. They won't, nothing will register because it's just another equation and there's so many of them, it's too hard to keep track. However, if you're on top of these double replacements,
Louis Pasteur.
yeah, Pasteur, okay, thank you. However, if you're on top of these, then you'll notice, hey, there's something strange about this particular equation, right? And there's a reason why it's strange. And in the normal sense, this is what we would have done. In the normal double replacement, we would have done this. We would have said, okay, A is CA2 plus, B is phosphate. C is H plus, and what is D?
SO4. Two.
Sulfate. And then we just use calcium and sulfate and hydrogen and phosphate. Hydrogen and phosphate is going to make H3PO4. And so they only stopped at 2 hydrogens. It's actually not hard to do. You just don't add enough sulfuric acid when you stop there. We would have gotten this. Is there a driving force for this? Well, one thing that the book doesn't do, the book is very sloppy about writing states. I don't know why.
Professor, can you explain how it's 3 instead of 2 in the hydrogen phosphate?
Hydrogen phosphate?
Yeah.
Okay, so we're taking hydrogen
Yeah.
and phosphate.
Mm-hmm.
So how many hydrogens do we need to balance that out? We're going to need 3. Then it balances. Now, how do you form dihydrogen phosphate? We'll take a guess. How do you form carbon monoxide? You starve it of oxygen. So you can't go all the way to carbon dioxide, right? You starve it of oxygen. How do you know you've starved it of oxygen? How can you starve it of oxygen? Well, you close the barrel. Well, tell me, how many screws should I turn the barrel in to get a lot of carbon monoxide? You know? No, it's very difficult. And so what we do instead is this, is we don't worry about these intermediate, we just react it all the way. In metathesis, we're going to react it all the way. We're not going to stop halfway because I don't know what conditions that requires. We're just going to go all the way. And so when we do this one, we do it all the way. And so our prediction for this is just an AB plus CD, right? And then you might have, I don't know, did you notice it looked weird or you didn't notice it looked weird? It depends on your familiarity. You know, like they said, chance favors the prepared mind. The prepared mind is something you recognize. Is it familiar? Oh, this is unfamiliar. This is different. You know, it depends on how many of these you've done. The more of you, this is why I assign such a huge set of homework, because that's to gain familiarity. How do you get experience? Well, people have been working, you know, people work 30 years, how do they get that experience? They get experience slowly over the years. Well, we don't want to wait. Do you want to wait 30 years to finish this class? No, God, no. Right. So what you want is you want to get through it quickly, right? To get through it quickly, you need to do a lot of problems in a short time. And then you'll have the exact same amount of experience as somebody who's been doing a few problems over a long period of time. And so and people who say homework is proven not to be effective or just making too broad of an overgeneralization. Yeah, maybe some homework assignments are totally ineffective, but not all, that's for sure. And so this one is, you know, you're familiar with this. Hey, this is a little bit weird. This one looks okay, but this one looks weird. You know, it's not an AB plus CD type, but it is. What they did was they just didn't give it enough H plus. They only gave it enough for 2. That's easy to do. You know what we call that? We call that the limiting reagent. Limiting reagent. Normally when we try to do these reactions, we do it stoichiometrically. You put in just the right amount. But sometimes we don't put enough of one or the other, or we put too much of one. Too much of one is called the excess reagent. We're going to be talking about limiting reagents and excess reagents. So if we limit the amount of H2SO4, then we can make the dihydrogen. If we limit it even more, we can make the monohydrogen. You know, And so we can adjust the conditions to get this. This is a big thing. This is what makes a lot of people fail organic chemistry, because you have to keep in mind all these little things that, and in organic chemistry, you have to memorize a lot of information. You know, the conditions, temperature, concentration, and picking the appropriate oxidizer. You have to have a whole database of oxidizers memorized so you can pick the right one. You know, do I need a mild oxidizer? Do I need a strong oxidizer? This kind of stuff. The same thing with reducers. You know, NAD is a reducer. NADH is a reducer. NAD is a oxidizer. You know, there's different strengths and this kind of stuff for biology. You know, it's really important. Getting back to this is what we would have predicted. Would there be a driving force for this? Maybe there was no driving force for this. Was there a driving force for that? Obviously there's a driving force for that because the reaction occurs. That's how they make it. But is there a driving force for this reaction here? And so what is calcium phosphate? Solid, liquid, gas, or AQ?
Solid.
Solid. H2SO4?
Aqueous.
CaSO4.
No, aqueous.
Sulfates are all soluble except for,
Calcium, strontium, body.
yeah, it's solid.
Okay.
It's a solid. H3PO4.
Aqueous.
Aqueous. Good. And so, can we say the driving force is precipitation?
No, because it goes from one precipitate to another precipitate.
Yes, we can't. We can't, because this is one of the first examples I did where one precipitate sacrificed for another precipitate. Now, at this level, since you memorized the solubility rule, at this level, you might be able to tell me which of these precipitates you expect to be more stable, more strongly bonded. Would you expect calcium phosphate to be more strongly bonded or calcium sulfate to be more strongly bonded? What would your guess be?
The first one.
The first one, yeah.
More charged.
Yeah, exactly. Good, good. I would have predicted calcium phosphate is more stable, so in fact, this I would expect not a good driving force at all. But all we need is one driving force. So if there's something else, you know, then we would look at it. And so, yeah, calcium phosphate should be more stable. And so, is there another driving force that you see for this? Well, what are the other driving forces for metathesis?
Acid.
Stronger, it doesn't have to be strong, it just has to be stronger. Stronger to weaker acid. And so, what is H2SO4 compared to H3PO4? Which one's stronger? Yeah, so this is stronger acid to weaker acid. And this would be our driving force. Precipitation of calcium sulfate I would not put down because calcium phosphate. Sometimes it's hard to tell, but in this case it's probably right. You're probably right because of the charge. Yeah. Also the solubility rules, you know, phosphates are all insoluble except for,
Group 1 and then group 1.
however, sulfates are soluble. So most sulfates are soluble except for
calcium, barium, strontium, and also
Silver.
mercury,
Yeah.
bromine, mercury 2, silver, and lead.
and lead too. Good, very good, yeah, good. And so sulfates are a heck of a lot more soluble because of the charges. Okay. Other factors too. Charge is just a simple one. Okay, the other thing I wanted to talk about this is this. Your book doesn't write the states, but you're required to write the states. Also, we want, this is the CE. We want to do the IE. What is the IE for this?
3 calcium, 2 plus.
3 calcium 2 plus?
And then
Did we say that this is a strong lattice or weak lattice?
No, we did not.
Did we say this is a strong lattice or weak lattice? That is, if I put this lattice, in other words, if I put a crystal of this in water, will the water tear it apart
No, that's
and
not
dissolve
strong.
it?
No, that's not strong.
It's a strong lattice, that's why it's a solid. And it stays a solid, so we don't tear it apart. Water can't tear it apart. And so this has got to stay, not that, it's got to go to
CA3PO.
Ca3PO4 2. solid.
That
Okay,
one's-
now will water tear apart H2SO4? Yes, but this is going to be very tricky, right? Because water, there's two hydrogens. When there are two hydrogens like this, we call it a diprotic acid. Water doesn't take both hydrogens off at the same time. What water does is it plucks one hydrogen off first. And so one hydrogen comes off as a H plus, leaving HSO4 minus. Now, H2SO4 has just lost one hydrogen. It has one hydrogen remaining. Is it going to hold on to that remaining hydrogen more tightly, or will it just lose it easily?
More tightly.
It's going to hold on to it more tightly. In fact, is HSO4 minus a strong acid or a weak acid?
A weak acid.
It's a weak acid. And do weak acids lose their protons easily?
No.
No. And so this is what happens in water. In water, we do not form this. And so H2SO4 in water does not go to 2H pluses in a sulfate. Water has no problem taking off the first one, but it has a problem taking off the second one.
So it's gonna be water.
And so it's going to be H plus and HSO4 minus rather than two H pluses and a sulfate.
Will something like this be on the test?
No, this is, something like this will be on the final. But this is, I'm trying to keep the test easy, or with the equations, and not do too much initially. So this is why we spent so much time just doing the basics. So, well, doesn't that mean we should form calcium bisulfate rather than calcium sulfate? Because if water can only tear off the first hydrogen, then we just have HSO4 minus, so shouldn't we form calcium bisulfate? And the answer is no, because what's going to happen is the calcium ions are very aggressive. They're 2 plus. And the calcium ions are going to come in and knock the second hydrogen off. Water couldn't pull it off, but calcium is going to knock it off. And therefore, it's going to form a much more stable product. And so water will pluck off the first, calcium will get the second. Calcium gets a second, we're going to form calcium sulfate. This is a solid, so that means the lattice is strong, and water is not going to break that apart. How about H3PO4? Is water strong enough to pluck the hydrogen off? No, because H3PO4 is a weak acid. And so the IE and the NIE are the same because there are no spectators in this reaction. And so the interesting thing about number 77 is this isn't what we predict, but you know, we can expect stuff like this to happen. We can expect stuff like this to happen depending on the conditions. But are we expected to know? We aren't expected to know this. So what are we going to do? We're always going to go all the way to the end. Where's the end? And so that brings us back to chapter 9, number 27. If we go back to chapter 9, number 27, this is the end. When ethanol is oxidized in your body, if you drink an alcoholic beverage, right, ethanol is going to be oxidized. And it's going to be oxidized in steps, but eventually, no matter how many steps there are a lot of steps, you know, because when I was taking biochemistry, I had to memorize the Krebs cycle. You know. But there are a lot of steps in the metabolism of ethanol, but all we care about is where it's going to end up. And so if you drink ethanol, where does it end up? It's going to end up as CO2 and water. And so in this case, we're going to burn ethanol in our body. We're going to take ethanol plus O2, which yields CO2 and water. Are we going to be exhaling soot? Are we going to be exhaling carbon monoxide? No. We're going to, yeah. We might be vomiting acetaldehyde, but that's a different story. We weren't going to make those predictions. And therefore, when we do metathesis, we don't stop at bisulfate. We go all the way to sulfate. We don't stop at monohydrogen phosphate or dihydrogen phosphate. We go all the way to phosphate. Every semester, though, somebody will stop. You're going to have chemical reactions on the final. They'll be a little bit more advanced. But you know, every semester people will stop like this. You know, maybe they'll do monohydrogen phosphate or dihydrogen phosphate. Maybe they'll do hydrogen sulfate. This one's kind of weird because on one hand they did this partial, but on the other hand they didn't do this partial. You know, and so it's weird. We could have gotten a lot of product, and so the easiest is just to do it all the way. So anyway, this is a stoichiometry problem, right? And stoichiometry. Did you guys calculate this? Did anybody get it? No? Well, what information do you need? Okay. Well, do you guys have a lot of questions on the practice test, or? All right. All right, then why don't you work on this one? You can work on this one at home then, if you want, or if you have more time. I don't want to get too far. I'm already kind of far behind. But
Is chapter 10 is going to the test?
no chapter 10 on this one. But we still have to cover chapter 10, otherwise we're gonna run into a problem. And since I don't have chapter 10, you gotta expect at the end of the semester we're going to be crunched for time because this. If you're okay with being crunched for time, then I'm okay with covering this.
Yep.
All right, which problems do you want to take a look at? 10?
That's false, right? Because copper is a positive charge.
Copper is neutral. And that's not the reason we use.
Does it have a variable charge? Doesn't copper have a variable charge? Or is it always neutral?
Okay, the copper in a copper penny has positive charge. The copper in a copper penny has positive
No,
charge.
I don't know. I thought copper was variable.
Copper ion is variable. Does copper metal? They make the pennies are made out of zinc and copper. Zinc is in the middle, copper is on the outside. Is the zinc in the inside 2+ and the copper on the outside 1+? Or 2+? It's variable charge, so maybe it's 1+ or 2+. Well, it depends. It depends. Brand new copper penny is going to have a coating of copper metal. What is the charge on copper metal? Okay, let's show.
It should be 2. Because zinc is 2+. Otherwise they react.
Copper is an interesting metal because, did I talk about aluminum? Can they mine aluminum metal out of the ground? No, all the aluminum in the ground occurs not as the metal, it occurs as most of the aluminum comes from bauxite.
From what?
Bauxite. This has a lot of names. This is called aluminum oxide or alumina. Its trade name is alumina. I used to buy this all the time. I used to buy alumina cookware. Alumina cookware because it can withstand extreme temperatures. They also use it for other things. For alumina, if you get single crystals of it, they use it for goggles for nuclear bomber pilots. Because it's extremely tough material. And then they dope it with certain things, so it can go from clear to opaque, or not even opaque, just completely block out light in microseconds. Is it? I don't know. Opaque, can you see through it?
No.
No? Okay, opaque. It would go from clear to opaque. Microsecond. But the person who figured out how to get aluminum metal from bauxite became one of the richest people in the world at the time. There's a documentary about this guy. Did I talk about this?
No.
Oh.
Wait, so can H plus react with copper metal? No, right?
Hmm?
The answer is false, right?
Yeah, but if you don't know the reason,
But isn't it because it has no oxygen to oxidize?
no. That's not. If you don't know the reason, then I throw on a different question and you memorize this one. You know, are you going to be able to figure out the next one? Will H plus oxidize lead? True or false? Will H plus oxidize zinc? True or false? Zinc, because you did that. You did that in the lab. Will H plus oxidize silver?
Yes,
See,
but.
the arguments that you're using are going to get you nowhere. You have to understand a little bit more in order to be able to to answer this. So I could just change this question easily, and you tell me the reason. Or I'll just, it depends. I'll just play it how you guys want to do it. If you just want the answer, I'll just tell you the answer. The answer is false.
Why?
Why? I wanna know why.
You want to know why?
Yeah.
There's no driving force. That's why.
That was it?
Yeah.
So how
But that's not enough, you know.
And what's the enough answer?
What is the driving force? I asked you the chemical properties of H plus. Do you remember that yesterday? The HCl? What were the chemical, did anybody write down the chemical properties of H plus?
no, it was just
One, you could memorize them, or two, you could
Pattern.
look for patterns so you don't have to memorize them. I tried to show you the patterns so you wouldn't have to memorize them. But did anybody write down the chemical properties of H plus?
it'll react with anions that are stronger based than water.
Is that the only one you wrote?
It oxidizes all reducing agents stronger than H2.
Yeah, okay. So H plus will oxidize all reducing agents stronger than H2. I asked you this, and I tried to make a big point, a big fuss over this. Is chloride the same as chlorine?
No.
They're on totally opposite sides. They're doing two different things. If you tell me that copper is the same as copper 2 plus? No.
No.
This is like Dr. Jekyll and Mr. Hyde. When I ask you the charge, it's so important. Charge is so important in chemistry. This is why electrical forces are the most. And so the charge makes all the difference in the world. I'm asking you, what is the charge on copper metal? If I have a piece of copper metal, is it on this side or is it on this side?
That side.
It's on this side?
No.
Oh, no, that's copper ion, sorry. Copper metal is that one.
The right side.
Then you gotta know what you're talking about first. And when we're talking about copper metal, are we talking about copper ion? On the surface there's a black coating. A brown coating first forms. This brown coating eventually turns black. The black coating is this. Does this look like copper at all, this black coating on here? What color is oxide?
Black.
No, oxide, dihydrogen monoxide. What color is oxide?
Clear.
Colorless. What color is copper 2? Well, this is what's giving it this black color, right? It's the copper 2 in here. It's either blue, can be black, depends. Does this look anything like this?
No.
Do copper 2 ions behave anything like copper metal?
No.
So what are you telling me? I'm asking you, what is copper metal? Is copper metal copper 2 ions, or is copper metal copper metal?
Copper metal.
This is copper metal. What's the charge on copper
Zero.
metal? 0. Although that's some, I don't know what's on there, but that's no charge, that's nothing. Right. And so what is the charge on copper metal? 0.
So H plus cannot react with copper metal because there's no charge.
No.
Oh, so it's not stronger because it's not stronger than H2. Okay.
So then do all metals have no charge?
Yes.
All metals have no charge. Lead metal has no
They
charge.
won't react with any
All
metal.
ions have a charge.
Metals.
Metals are elements. Do elements have charge?
No.
No. No. This is just getting familiar with this. You know, the more you work with this, the easier. So we're trying to cram a lot of years of experience, but the thing is, it means having to cram it in. You have to cram it in.
So this is all ions on the left and
Yes.
Yeah, that's one of the patterns. Is it all ions on the left? No, you got ions on the right too. You know, but what's special about those ions? These are the patterns you look for. A lot of people look at this and go, it's too much, they don't want to deal with it. It's okay. If it's too much, you don't want to deal with it, you don't have to deal with it. Because like I said, of course, if you understand this better, then you can make predictions. For example, platinum's not on this chart. And so if you know a little bit of chemistry, you can make predictions. Versus if you taught this to an elementary school student, did I mention this before?
Yeah.
You don't need to know any chemistry. You could teach this to an elementary school kid, and all they have to do is position it, right? That's it. However, they wouldn't be able to tell me what platinum doesn't occur on the chart, and so platinum's not on the chart. They can't tell me anything, right? Whereas if you knew a little bit more of the chemistry, you can make a lot more predictions. What else doesn't occur on this chart? A whole bunch of stuff doesn't. Is perchlorate on this chart?
No.
No, but where would you predict it would be? You know, well, iodate's on this chart. Would you predict perchlorate to be stronger than iodate or weaker than iodate?
As a what? Reducer and oxidizer.
Well, what do you think it's going to be? Is it going to be an oxidizer or reducer? Is perchlorate electron rich or electron poor?
Electron poor.
Electron poor. Iodate's on this chart. I'd expect perchlorate to be higher or lower than iodate? Higher.
Higher.
So these are the types of things we're trying to look for in terms of patterns and this kind of stuff. You know, this is why we talked about the charge. We look for these patterns. Like ammonium's not on this chart. Ammonium's not on this chart, but you would know it's a pretty good reducer or pretty good oxidizer. Ammonium's got a positive charge.
so it's an oxidizer.
It's a reducer.
Why is it a reducer? Because don't the oxidizers gain electrons?
Oxidizers gain electrons.
So then why wouldn't that want to gain electrons because it's positive?
In one sense, yeah.
So then why is it a reducer?
Did I mention this yesterday?
No.
Day before? Do you guys remember the Grand Camp? I guess I didn't show you know what? I missed part 1 of that video. Let me see if I can just jar your memory a little bit. Oh, not this one, sorry. Shoot. I guess I think I have my history.
Professor, is combustion considered a type of chemical reaction, or is it
Yes,
just the 4?
it's a redox reaction.
Okay, so 4 would be false.
So oxidizers are electron poor. That's true.
Well, do you guys remember Texas City?
Yes.
What happened there? What was that ship built with? If you go back like 2 days, I wrote why ammonium. Ammonium, everybody predicts that's an oxidizer. That's wrong. You go back 2 days in your notes and you'll see it. It's the exact same reason perchlorate is a powerful oxidizer. A lot of people will say perchlorate's a reducer. Perchlorate's a reducer because it's got a negative charge. It's a reducer, it's got electrons to give up.
But it's actually stable.
It's actually an oxidizer. It's extremely powerful oxidizer. I talked about perchlorate numerous times that it's an oxidizer even though it has a negative charge. When you look at the chart, you know, these are the patterns you see at the chart. When you read the chart, you'll see a lot of contradictory things.
Aren't there the exceptions though?
These contradictory things, you don't have to understand to use the chart. You can completely ignore it. So there are different levels you can hit this at. One, just be able to follow the steps. If this is too much, just be able to follow the steps like an elementary school kid would. You don't have to understand it. But for the people who want to understand the confusing things about the chart, then that's why I talked about it. But if you can just follow the steps, step 1, inventory, step 2, pick the strongest oxidizer, step 3, pick the strongest reducer. If you can follow those steps, then no problem, you're going to be okay. But to answer more advanced, more challenging problems, then you have to understand more. And so I could go into the advanced or more challenging, but if you aren't getting the basics, then you need to practice the basics because the basics aren't that hard. A lot of people will say, oh, that's too much, but it's not. It's pretty easy. The basic steps, that is. And so just give it a try.
So this is actually electron rich because nitrogen is -3 and that's where it wants to be, so you have one extra proton because
No, it doesn't necessarily want to be at -3. -3, this is why I said the charge. For example, -2 on carbon is totally different. This is why I did ethanol. Yeah, I did the ethanol combustion earlier. C2H5OH or C2H6O. Ethanol is very flammable. Ethanol reacts with the traditional oxidizers. They call it oxidizer because of oxygen. Oxygen is the most common, the cheapest oxidizer we have around. Ethanol has carbon in the -2. Oxygen is -2. So shouldn't water be electron rich like ethanol? If oxygen is -2 and ethanol has carbon in the -2, then water should burn. No, because this is where you have to do some additional memorization. You have to have these reference points memorized. Oxygen is happy. This is why I use the term happy, unhappy. Oxygen is happy at -2. Is ethanol very flammable?
Yes.
Ethanol is very flammable, which means carbon is not so happy at -2. And so we need these little reference points to understand. You can't just say, oh, it's got this charge, or it's at where it wants to be. Where it wants to be depends on what you mix it with, and it depends on your understanding. Now, nitrogen at -3 is a lot less stable than an oxygen at -2. An oxygen at -2 is less stable than a fluorine at -1. Fluorine at -1 is very stable. But oxygen is very happy at -2. Now, nitrogen at -3 is a lot of electrons to hold on to, so it makes it a little bit less stable. You know, it's like somebody carrying a pot of gold. You know, they got too much gold in there, and then they're going to be too unstable. Even though, yes, of course they want it, but it's too much to hold on to. 3 extra electrons is a lot to hold on to.
But that's the reason it has an extra proton, because nitrogen, at least according to the part that we learned from the start, because it's 1, 2, 3 away, -3.
Yeah,
So
-3.
it's happy
So,
at -3.
so the thing we reference it to is something like methanol. Is methanol highly flammable?
Yes.
The charge on carbon in methanol is -3.
Mm-hmm.
How about ammonium? Ammonium, is it highly flammable? It turns out ammonium is pretty flammable. Not as flammable as methanol, but pretty flammable. This is at -3. You think -3 would be happy and stable, you know, but there aren't. Are there a lot of nitride compounds?
No.
There aren't a lot of nitrides out there, and most of the nitrides aren't that stable. Although there are some that are very hard materials, but.
But out of all the charges you could give to nitrogen, that's the best one for it. That's the most stable of the nitrogen charges, right? because of the range?
No, that's gonna be at the upper limit. So for example, carbon, what are the limits of charge on carbon? Okay, oh, methane's -4. Oh, that's where it wants to be. Carbon wants to be at -4. So if I fill this room up with methane, carbon's happy as is, correct? Because carbon's at -4, it wants to be at -4, it's at the range, right? It's not happy. These are things you have to memorize atom by atom, and so this is like, you can't, this is something that you can't make simple generalizations for. It's a bit more complex. So this is stuff that takes a little bit more work to work, because what you have to do is you put that 30 years and you have to memorize little facts here and there. You memorize the little facts by comparing. I would say CO2. Is CO2 pretty stable?
Yeah.
Yeah, based on experience, CO2 is pretty stable, so I'd say +4 is happiest for carbon. Carbonates, are carbonates happy? That's because we live in an oxidizing environment. Now, if we're on Jupiter or some planet, if you get into like astrochem, if we live on a planet with a reducing environment, then, like for example, where is it? There's some moon off Saturn or something, is filled with methane. That means it's a reducing environment on the planet. And so it depends. The Earth is actually, according to geologic history, the Earth is cycled from an oxidizing atmosphere to a reducing atmosphere to an oxidizing atmosphere. And so, it's cycled. And so there are bacteria that thrive on this and bacteria that thrive in the oxidizing environment. So it depends. It changes depending on the atmosphere you work on. So for example, aluminum, metal is not stable in an oxidizing environment. Aluminum metal is going to be oxidized to aluminum 3+. However, copper metal is stable in an oxidizing environment, this oxidizing environment. It's not 100% stable, but it's a lot more stable than aluminum. You can find crystals of copper. Gold is quite stable. It depends on the environment. Now, if you change the atmosphere, if you put copper in a fluorine atmosphere, forget it. Then the plus is going to be the most stable. And so we do it case by case, and the case by case requires a lot of memorization. You don't memorize it all at once. This is why I bring up little points to memorize as we go along. Hopefully you pick some of those up, and then we do it, and then I try to use little terms like happy or unhappy. And so this is much more advanced. You don't need to necessarily know this for this test. Some of these stuff you might, like on this I asked, did I ask on this test about ammonium? No, I asked for chloride on this test. Number 6.
Yeah, that one was true.
No, it's false.
Perchlorate is a negatively charged ion that is best classified as electron poor. That's true. So there you need to know some more. I'm not asking you how unhappy it is, but you know it's terribly unhappy. Why? Because chlorine is in the +7, which makes it even worse than iodate. And so going back to this chart, we could easily position perchlorate as above iodate. Iodate is plus, what's the charge on iodine?
1 minus 1.
Oh, no, in iodine and iodate.
Oh, iodate. 2 plus?
No,
3 plus? 5?
no, 5+.
Oh.
And so, and not only that, iodine's much bigger. And so if you have a 5+ charge on a big atom versus a 7+ charge on a small atom, which one's going to be more reactive? The small atom. And so perchlorate's way up here. This is why chlorine, you might wonder, why is fluorine at the top? Why isn't it like bromine or iodine? It's because of the size. Fluorine's small, chlorine's bigger. Bromine's bigger, iodine's biggest on this list here. It's because of the size. These are all these little patterns that, there are a lot of little patterns in this. And this is why, my analogy to looking at this chart is spreading out all the papers on the floor and just staring at it. But you don't want to just stare at it. What you want to do is you want to read through it, name these, and then get familiar with it that way.
Can you do number 9, please?
Well, getting back to this, remember we did the chemical properties, I'll do number 9 in just a second, but we did this. And I did this verbally. Can H plus oxidize lead?
Yes.
No.
No. Yes.
Yes.
Metals can't be oxidized. You just said that.
Metals can't be oxidized? What is this black coating on here?
The ion, the copper 2 ion.
No. Did the penny start off as copper 2 ion and it was oxidized?
No.
Metals, what about iron? Does iron rust?
Yes.
Metals are oxidized. Metals are oxidized.
So then why is copper oxidized?
Copper is oxidized.
Yeah.
Copper is oxidized. But not by H plus. Copper is oxidized by O2. O2 is a heck of a lot stronger oxidizer than H plus. Here's H plus. Here's H plus. Where's O2?
Right there.
Way up here. O2 can easily oxidize copper. Boom. What does it form? Copper 2. We did this chart yesterday. Remember that? How to use the chart. Make predictions. Lithium ion is lonely. What can lithium ion oxidize on the chart? Nothing. All right, number 9.
Yes.
The oxidation state on nitrogen in ammonia. Oxidation state is the charge. So the charge on nitrogen in ammonia is -3.
Okay, and I got that by adding the H pluses, so that's +3, and then you want that to equal 0, right?
Right.
Okay.
This actually is a lot more complex, but we're taking it in steps. First, we're going to learn about oxidation state. Then we're going to learn about formal charge. After that. And so it's going to get more complex with the charges. Because this is not an ionic compound, so these aren't real charges. These are charges used to predict redox behavior.
Yesterday you mentioned that we weren't going to need to know the ic-us endings, but on the practice test, under section 2, there are a bunch of the phosphoric acid, chlorous acid. Can you go over the endings for those?
No, the ic-aus is for the old versus the new naming system. There are 2 ic-auses. You need to know ic-aus for acids. The question was about the old naming system. And the lab. The lab had a whole bunch of things like this. Stannic. Cuprous. What I said was you don't need to know. Tell me what stannic is. What's the charge? Tin 4. So you don't need to know that. Stannic is tin 4. What is cuprous? Copper 1. That's what I meant. This ic-aus is for the old naming system for the ions. For the acids, it's not ic-aus. It's hydro, ic, acid. It's ic, acid, and it's aus, acid. I wrote down acid in those. We don't have to write ion here because if it's like this, we gotta assume it's an ion. So, like, if it's iron 2, that's gotta be iron 2 ion. If it's sodium, then it's ambiguous. We don't know if that's sodium metal or sodium ion. And so we have to write down the word ion. I mentioned this a long time ago. So we need to know this for sure. But the question wasn't about that. The question on Piazza was about our lab. And our lab is, at least the first question was about our lab, and our lab was the for the ions, the cations, the old and the new naming system. Still, we want to do it in the lab so that you've heard it before. You know? And still, a lot of old bottles are marked ferric chloride or ferrous chloride or ferrous sulfate.
Professor, I have
Uh-huh.
a question.
Uh-huh.
Nitrogen charge is between -3 to 5, right? It can
Yep,
be-
right.
So why in number 9 it's -3? Why isn't 3 just after equal to 0? So hydrogen can be positive one.
Because there's 3 hydrogens. You know how hydrogen has a +1 charge?
Yeah.
There's 3 of those. And then you want equal to 0.
Oh,
Yeah.
yeah.
Okay, remember NOx? You guys remember that?
Yes.
Okay. If we burn, you could, okay, acid-base properties of ammonia and ammonium are totally different. Acid-base properties. This is an acid, this is a base. But actually both, this is amphoteric. But redox, these are the same, because both of these have -3 here. And so if we burn these in oxygen, we could do partial oxidation, or we could do complete oxidation. If we do partial oxidation, we might form something like nitrous oxide. Nitrous oxide is laughing gas. And we might think, okay, let's try to burn, you know what, I'm gonna burn some ammonia cleaner and try to form some nitrous oxide, and then we could have a nitrous oxide, whatever. But that's very dangerous, because if you try to get laughing gas by burning your ammonia, you might actually burn it to NO, or you might burn it to NO2. Do you remember that guy was saying that there's a beautiful red-orange smoke
Yeah, and the
in the video?
Yeah.
That beautiful red-orange smoke is this. This is very toxic. NO2 is the beautiful red-orange smoke from nitrate fires. He said it had a real sulfury odor to it, but it's not sulfur, it's nitrogen-y odor to it. Etc. And so what are the charges? -3, what's the charge on nitrogen here? +1. What's the charge on nitrogen here?
+2.
+2. What's the charge on nitrogen here?
+2. No. 4.
+4. Where is it going to stop at?
8. No, 5.
It's going to stop at +5. And so we just figure out what is the +5 version of that, and then we're done. Nitrogen has variable charge. That's what we mean by variable charge, but which one is it going to form? Is it going to form laughing gas when we burn it, or is it going to form all the way? Well, we got to assume it's going to go all the way to +5. Otherwise, it's too hard to predict. Right? And the best way to do that, so we're going to give it vigorous oxidizing conditions. In organic chemistry, we do this. In organic chemistry, you write this. This is a symbol for oxidizer that you're going to mix in there, and you say mild or strong, you know, this kind of stuff. All right, what other questions do you guys have? You can just continue. What number? 5? Oxidizers are electron poor.
No.
It's true. Oxidizers are electron poor. All oxidizers want are,
Take electrons.
yeah, all oxidizers want to take electrons. They take electrons from what? Reducers. So oxidizers are electron poor, true. Okay, what else?
Can we do 27?
The molecule is determined to weigh 34 U. Could its formula be OH? What's the weight of an OH molecule?
Eight, 17, 18.
17. It can't be. If the molecule weighs 34 and this molecule weighs 17, they aren't the same thing.
So what's the difference between U and then gram?
U is per molecule, gram is per moles of molecule.
Oh, okay. So that is 17 U, but
Yes.
it weighs
It's 17 U per
per
molecule,
molecule.
or 17 grams per Avogadro's numbers worth of molecule.
Okay. Okay, so to get the gram of that, you just divide it by Avogadro's number?
No, to get the grams of this, the grams of a single molecule,
Yes.
to get the grams of a single molecule, we have to use the conversion factor.
Okay, yeah.
The conversion factor, one, you can memorize it or derive it. I derived it in class, but does anybody remember the conversion factor? How many U are in a gram?
12 U in 1 gram.
No, there's 6.022 times 10 to the 23rd U
Oh.
in a gram. When you remember, the 12 is how I derived it.
Okay, so that would be, so if you do the conversion factor, you would just put like 17U, so like in the numerator, and then in the multiply it by
Yeah.
1 gram per point.
Right, right.
Okay.
Then you can convert it, and it comes out to a very small number of grams.
Okay.
Okay, questions? 30?
The first 30. The first 30.
A compound contains 94.06% oxygen and 5.94% hydrogen. It has a mass of 34 U. Determine the molecular
So
formula.
I got H2O2, but that just doesn't seem right.
You got H2O2? That's right.
I don't reduce that to
It's a molecular formula. OH would be the empirical formula. Okay, what else? 17? Only one natural isotope of fluorine occurs. All atoms of fluorine in nature have the same mass number, exactly 19.
What about the radioactive?
What about the what?
Radioactive?
Radioactive isotopes? We don't have to worry about radioactive isotopes.
So if you know radioactive isotopes,
Yeah,
so that is true.
that would be true. If I eliminated mass, number, and replaced it with mass, then it would be false.
Okay.
Oh, no, it would be true too, but it wouldn't be 19. It would be a different number, 18.99, and it wouldn't be exact. The only atom we can weigh exactly is the one that's known by definition, which is,
The one in France. No, that's not it. That's the
it's
group.
not in France. The only atom we can weigh exactly,
Carbon.
carbon 12.
Then divided by the mass.
Okay, what else do you guys have? We could take a break and then come back, short break,
Okay.
while you look for more questions, or keep going? Keep going, all right, keep
Take a
going.
break? Can we take a break?
Oh,
Yeah, right. Oh.
Nothing. Oh, I'm done.
Can we take a break?
We can take a break, I guess most people want to take a break.
27.
What did you say for 21?
Yes. So, okay.
Oxygen,
So let's do
copper.
the common mass